Okay, so now what I would like to do is to run through with you an introduction to power systems. Here is a diagram that is representative of what we consider to be the structure of today's power system. The power system consists of generation, transmission, distribution, and then the customer or the end user. Traditional generation consists of large thermal plants, and today we see the proliferation of renewable energy type plants like wind and solar and so on. But traditionally, power was produced or provided by large thermal plants such as nuclear, coal, and other renewables such as hydro and geothermal and so on. Right, so that all of that is considered to be generation. The generation plant is usually connected to the transmission system, which is an interconnection of high voltage lines, right? And usually to get from the generating to the transmission level, there's usually what we call a step-up transformer that step the voltage up from a low voltage at the generating site to a high voltage for the transmission of bulk power, right? The transmission level voltage is usually then stepped down by another transformer, a step down transformer, and at this step down or lower level voltage is then distributed to customer at different levels. These could be commercial level type customers connected to what we consider to be the sub-transmission network, or large customers connected to the primary of the distribution network. And then you have household or residential type customers connected to the secondary at very low voltages at 120 and 240 and so on. Transmission is usually done at high voltage in the range of, let's say, between 138 to up to 1100 kV across the globe today, right? And the reason for doing that is that you transmit the power at higher voltages, lower currents, and therefore less losses in transmission along the path. There are in some cases very large customers that are usually connected to the transmission system at 138 kV and so on. So let's look at some of the type of generation, right? So generation, we look at different prime movers, and prime movers in the sense of the source of power that is driving the electrical generator or the electrical generation. So we look at nuclear, coal, liquid fuels, gas, there's a natural gas, hydro, geothermal, wind, solar, and other forms of renewable energy sources. In addition, in a generation plant, you will have what we call the energy conversion system, which in most plants is a synchronous machine. And when I say energy conversion system, I'm really referring to the system that converts the energy from the prime mover to electrical energy that can be transmitted and distributed across the grid. In few cases, you have induction machines, and in those particular cases, it's specific to, let's say, wind power. And as we go into those topics, you'll see the application of induction machines in wind turbines. I also include here inverters, as in the case of solar PV and wind power plants that utilizes inverter technology. In the power plant or in the generation aspect of things, there's also the supervisory and control and protection systems that looked at how the generation plant is operated and controlled within the design limits, right? In terms of transmission, the different components of transmission includes substation or substations, So in a large interconnected grid, you'll have multiple substations. In the case of TNTech, we have approximately maybe about 150 or 120 to so substations. Substations usually consist of transformers, bus bars, breakers, disconnect switches, etc. In terms of transmission and distribution systems, you have what you call lines and feeders. So lines and feeders could be broken up into overhead lines, underground cables, right? So this picture here is a representation of what we call overhead, considered to be an overhead line, versus underground cables which are installed beneath the surface of the earth. In addition, you have systems such as compensating systems such as reactors, capacitors, SVCs, and STATCOM. And these are systems that are considered to be auxiliary systems that are required to support the transmission of power across the network. You also have the need for supervisory control and protection systems for the grid, separate and apart for those systems that are utilized in the power plant. In terms of power system elements, the load itself, which is the end user or systems that are part of the end user's system, such as, so we look at different class of loads. So you look at industrial loads, commercial loads, and residential loads, and the characteristics of the different load classes tend to be dependent upon the type of equipment that are used in those class of loads, such as large induction motors and other motors in electrical furnaces, and lighting that are specific to industrial application. And you're looking at the commercial aspects, which is predominantly dominated by medium-sized motors, heating and lighting, etc. Residential is more for small motors within household appliances like blenders and so on, fans, AC, heating and lighting and cooling, etc. In terms of the power system and its objective, the main objectives are to generate enough electrical energy from the most adequate power generation source or resource, right? And then to transmit this energy in large quantity to the load in an efficient, cost-effective, and reliable manner. And thirdly, to distribute to the end user in a safe, reliable, and cost-effective manner with the highest possible quality. So these are just some of the main objectives that form the basis of modern power systems today. In terms of power system networks, we look at the HV network, or the transmission system. Is usually an interconnected system. The purpose of it is to basically export or transmit or ships large quantity of power over great distances, right? It allows for the sharing of resources, so you could have multiple generating resources, different type of resources, wind, solar, thermal, plants, hydro, connected to a large transmission system, and therefore sharing that single resource, which is the transmission grid, right? Improving reliability, because you have multiple paths generally in a transmission network, it tends to be a lot more reliable than, let's say, a distribution network. And also there's the existence of economies of scale because of the interconnected nature. It presents that opportunity for greater economics. Medium voltage network, or the distribution network, is generally a localized network. You generally have multiple or numerous systems, independent systems. Economics of simplicity is the governing law or governing rule in that case. They typically single feed and have many load points and therefore have low reliability. It allows for autonomous operations, right? And when you look at loads, we did already discuss this. The loads are based on the categories, whether it's industrial, commercial, and residential loads, right? And this here just kind of give you an idea of what a typical distribution network looks like in a geographic kind of representation. This diagram just shows a representation of a power system or a model of a power system. These heavy lines are representative of what we call bus bars, or you could call them substations. And these lines here, for example, are the overhead lines or underground cables connecting the different substations. And these circles here represent power plants. In this case, we have a 200 megawatt power plant connected here, and another power plant on this side. This line with the arrow at the tip is representative of a load, maybe an industrial load. In this case, we're looking at 200 megawatts and 100 MVAR, megabars. Here we have a capacitor connected to this substation, and this element here is a transformer, where in this case we're stepping the voltage down from this bus bar to a lower voltage here at this bus bar, where then a load is then connected. Right? And this is a representation that you're likely to see in a commercial grade simulation software. Power system generation and load balancing. Basically, power is generated on demand, so it's only generated when required and as required. The load and the activities of the users obviously varies continually. This varies hour by hour, day by day, and season by season. Right? Generation and load must be maintained in a balance, and any imbalance affect the frequency of the system. Generation is dispatched in 3 categories or sectors or segment of the day considered. These are called base load, intermediate load, and peak load. And the diagram here shows the different sectors or timing of the day and what part of the load profile. So this line in red is representative of the load profile, and it shows what portion of that load profile can be considered base load, intermediate load, and peak load. Power system structure. So we look at power system restructuring. So given the emergence of new technologies, we see in the emergence of the smart grid concept, and this looks at both the SCADA, which is this supervisory control and data acquisition systems that are typically used in transmission grids and power plants, and coupled with that, automation type systems. We also see the emergence of microgrids, example for islanded applications or operations, and other new technologies to generate power, such as renewables, and in particular distributed type renewables and other type of distributed generation. We look at the transport power. So we look at technology such as HVDC, power electronics and superconductors. We look at energy storage, fairly modern a new technology to the grid. Energy storage in terms of fuel cells, battery, and other type of technology such as flywheels and so on. Pump storage, which pump storage is not so new, but there are new forms of pump storage, and we look at to save energy, so technology to save energy such as more efficient design and materials, right? Power system planning and operation. Practical power system planning and operation must be safe, reliable, and economical. Right? That is the three fundamental things in planning and operating a power system. In terms of the analysis, power system analysis, that is necessary for planning and expansion. So if you want to plan the expansion of your power system, then you have to carry out power system analysis. There are different types of analysis, and it's also used in the operation aspect as well. So some types of power system analysis includes power flow analysis, generation adequacy and reliability assessments, fault analysis, transient studies, quasi-dynamic analysis, and economic generation scheduling, which is more operation component.